Atoms are tiny, too tiny to be able to count, or even, until fairly recently, even to be able to see individually. The mass of nitrogen, for example, is 2.3 times 10 to the negative 23rd grams. So being able to mass out individual atoms in a lab is not a very realistic expectation. Instead, what we do is measure the mass of an atom by comparing its mass to the mass of another atom. For example, the red particle shown here has the same mass as 12 of the blue particles. This simply means that a red particle is 12 times heavier than one of the blue particles. Compared to the blue particle, the red particle has a relative mass of 12, and for any 1 unit of mass of the blue particles, the red particle will have a mass of 12. So the relative atomic mass is simply the mass ratio of one element to a standard atom. Since this is a ratio, the relative atomic mass has no unit. At present, carbon-12 is used for the standard of comparison for all relative atomic masses for several reasons. For one, it is a solid and can be easily handled. Its mass is easily measured in a mass spectrometer, and carbon compounds are abundant. So relative masses are assigned to new elements by comparing their masses to the carbon-12 isotope. These relative masses are what you find on the periodic table. When talking about single atoms or molecules, we can describe their relative mass in terms of atomic mass units. This is just one way to measure the extremely small masses of those individual particles. In reality, it is difficult to do calculations in terms of the number of atoms or molecules in a sample. These are tiny particles, and under normal circumstances, we cannot deal with single particles. For us to use samples in lab conditions, we need to use an enormous number of particles. This special number is known as the mole. 1 mole of particles contains 6.022 times 10 to the 23rd particles. We know that a mole of any sample contains 6.022 times 10 to the 23rd particles. This is a huge number, but we are dealing with tiny little particles, so really a mole of any given sample is a manageable amount. The relative masses on the periodic table can be expressed in terms of individual particles as well as in terms of the number of moles. These masses represent the mass of 1 mole of the element measured in grams. This is the key idea about the mole. It connects the atomic masses of the elements to the molar masses of the elements. So the mass on the periodic table can also be represented as the molar mass of the element. This is the mass in grams of 1 mole of the element. Looking on the periodic table, we see that the mass of 1 mole of carbon is 12.011 grams. The mass of 1 mole of magnesium is 24.31 grams. And the mass of 1 mole of copper is 63.54 grams. Information about atomic or molar mass can be found on the periodic table. Since it is a relative mass and therefore a ratio, it has no label. So the value recorded for the relative mass of an element can be expressed as atomic mass units when referring to a single particle, or it can be expressed in grams per mole when referring to a mole of particles. So find the molar mass of 1 mole of iron atoms and the molar mass of 1 mole of sulfur atoms. Iron is element number 26 on the periodic table, and here we find that the molar mass is 55.85 grams per mole. Sulfur is number 16 on the periodic table. Looking at the mass there, we find 32.06 grams per mole. Following that same thought, what if we had exactly 3 moles of iron? What would be its mass? Well, we know that the molar mass of iron is 55.85 grams per mole. This means that for every 1 mole of iron, we have 55.85 grams of iron. This is a proportion or a conversion factor. Since we know moles and are looking for grams, we want to use the conversion with grams over moles. So 3 moles times 55.85 grams of iron equals 168 grams of iron. So while 1 mole of iron contains 55.85 grams of iron, 3 moles contains 168 grams. We can also convert the other way. What if we have 100 grams of sulfur? How many moles are present in the sample? We can find the molar mass from the periodic table. Again, any molar mass is a proportion and can be written as a conversion factor. Since we know grams and are looking for moles, we want to use the conversion with the moles on the top and grams on the bottom. So 100 grams of sulfur divided by the molar mass of sulfur gives us 3.12 moles of sulfur in our sample. What if we have a compound as opposed to a single element? We saw before that the number of moles of each element within a compound is given by the subscripts. So let's say we have water. Water has a chemical formula of H2O. This means that we have 2 moles of hydrogen and 1 mole of oxygen for every mole of water in our sample. We can look up the molar mass of each individual element on the periodic table and multiply that by the number of moles in the compound. So hydrogen has a mass of 1.0079 grams per mole, and there are 2 moles of hydrogen in 1 mole of water. Oxygen has a mass of 15.9994 grams per mole, but there is only 1 mole of oxygen in 1 mole of water. So the total molar mass for hydrogen is 2 times 1.0079 grams, which gives us 2.0158 grams per mole. The total molar mass for oxygen is 1 mole times 15.9994 grams. This gives us a total mass of oxygen of 15.9994 grams in 1 mole of water. Adding all the elements together gives us the molar mass of the compound, which in the case of water is 18.0152 grams per mole. So what is the molar mass of glucose? Well, hopefully you remember that glucose is C6H12O6. The molar mass of carbon is 12.011 grams per mole, hydrogen is 1.0079 grams per mole, and oxygen is 15.9994 grams per mole. C6 means that we have 6 moles of carbon, H12 gives us 12 moles of hydrogen, and O6 means 6 moles of oxygen. So we multiply the molar mass of each element by the number of moles of each element in the compound. Adding those masses together, we find the molar mass of glucose to be 180.1572 grams per mole. What if we actually measure out 356.32 grams of glucose? How many moles would that be? Well, we just found the molar mass of glucose to be 180.1572 grams. Since we know grams and want to find moles, we will use 1 mole of glucose over 180 grams of glucose as our conversion factor. 356.32 grams of glucose divided by 180 grams per mole of glucose gives us 1.9778 moles of glucose. So some things to keep in mind about molar mass. The masses on the periodic table are relative masses. That just means that the mass is compared to a standard atom of carbon. For single atoms or molecules, masses are recorded in atomic mass units. This is a very tiny unit representing a very tiny fraction of a gram. For moles of atoms or molecules, masses are expressed in grams per mole. And molar masses can be used as conversion factors between grams and moles.